Hello, I'm thrilled to be here at NODES 2025, and I'd like to thank Neo4j for the opportunity to share some of my work with you today. For over a decade, I've been exploring how we can use graphs in ways that go far beyond analytics, but to actually run our business applications. Today, I'll share some of those concepts and show you what happens when we rethink how we build systems using a truly graph-native mindset. I'll start by walking through the key ideas and concepts, and then we'll see them in action in a demo application. I hope it challenges some of your assumptions and sparks new ways of thinking. We've got just 30 minutes, so let's dive right in. Over the past 10 years, graph databases have become one of the most critical data layers for analytics, extracting knowledge hidden inside structured and unstructured data. Graphs are powering systems such as fraud detection, recommendation engines, logistics, network planning, among others. With the rise of AI, graph RAG has proven to be one of the most effective methods for reducing hallucination and improving factual accuracy. What's becoming increasingly clear is that for the next generation of intelligent systems, data and knowledge can no longer live apart. However, for Graph to unlock knowledge across the landscape of enterprise applications, it still depends on structured data generated by other systems, most likely relational or tabular databases. This data must be ingested and transformed through data pipeline processes. This means that the graph typically represents a snapshot of the data at the point of extraction, not its real-time state. More recently, data lakes have narrowed this gap by allowing data to be stored in a single repository accessible to both operational and analytics systems. But the sequence remains the same: data first, knowledge later. No matter how much we optimize this process, data and knowledge are still treated as separate entities and created at different times. To change this, structured data must be created with knowledge embedded from inception. This requires a foundational shift, a move towards what I call graph-native systems. These are systems built from the ground up on the graph as their primary data model. The resulting graph will become a dynamic application graph, slightly different from a static knowledge graph that you might be familiar with. In this presentation, I will explore new approaches to designing and developing graph-native business applications that unify data and knowledge from inception. Over the years, I've learned that simply replacing a relational database with a graph database doesn't work. If we carry over the same approaches, mental models, habits, assumptions, and table-based logic to a graph, we'll rebuild the same limitations in a different technology that wasn't designed for them, creating new constraints. We can't think in terms of tables and data and expect to derive graphs and knowledge. To succeed, we must unlearn decades of relational thinking and relearn how to model, query, and reason, unifying data and knowledge in entirely new ways. This isn't just a shift in technology. It's a shift in mindset. To change our mindset, we must first understand the origins of our current one. Why do we use tables in the first place? Before digital machines, humans manually calculated tabulations, such as artillery firing tables. Early computers, such as the ENIAC, were designed to automate these repetitive, arithmetic, table-based tasks. This shaped the first programming languages, like Fortran, and core constructs, such as arrays, loops, and flow control, rooted in a table-first worldview. This computing paradigm was, and still is, extraordinary at solving the kind of problems it was designed for. It landed a man on the moon and brought him safely back to Earth. Hats off! It's so effective, so brilliantly suited to its purpose, that we never really imagined we might one day need an alternative. Despite decades of abstraction, we still design systems as if the world were composed of rows and columns, where we perform arithmetic iterations. This invites a provocative question. If our first problems had been interactive, relational, or networked rather than tabular, would we have developed an entirely different computing paradigm? Fast forward to today, and guess what? Most modern business challenges are networked and interactive. Around 70% to 80% of our business applications are workflows, as shown in this image. Yet our business applications still run entirely on a table-centric computing model designed 80 years ago for a completely different era of problems. Sure, it still works, just like you can still chop a tree with an axe. But as the trees become numerous and bigger, having bigger and stronger axes won't do the job. At some point, you will need a chainsaw, and our axe skills won't help. You need to learn a new way of chopping trees. A significant portion of these workflow business applications can run on a different computing model, leaving the legacy model for only the parts of the application that require intensive calculations. This is where graphs can play a crucial role, enabling these applications to think in terms of relationships, where knowledge emerges dynamically as systems operate. Graphs extend way beyond analyzing legacy data formats. This represents the computing paradigm we missed in 1945, but which is now ready to be embraced. To realize its potential, we must move past relational assumptions and adopt a graph-native mindset. Let's explore what this graph-native mindset is all about. Rather than compressing complexity into relational tables with primary and foreign keys, property graphs model the world as it naturally exists, as networks of relationships. While relational algebra relies on implicit set operations, union, intersection, difference, and Cartesian product, a graph-native mindset uses explicit ones, superset, subset, and element, aligning with how nature and humans intuitively organize reality into sets. From houses with rooms and closets to businesses with departments and business units, or the file systems in your computer, even our entire macro and micro universes, everything is organized as explicit nested sets. Graphs capture this structure clearly, intuitively, and in a way that is universally understandable by both humans and AI systems. Adopting a set-oriented mindset in graph modeling means defining entities by their semantic roles and organizing them into collections. That is, some entities will act as parent nodes, representing collections that aggregate related entities, effectively normalizing one-to-many relationships through explicit containment and membership. The purpose of using nodes as collections is to align the graph structure with the domain expert's mental model, even at the cost of additional traversals. So yes, collections could be replaced by direct relationships or adding different labels to nodes. But this design improves model clarity and usability besides normalizing one-to-many relationships and keeping nodes lean. For example, a key chain node groups multiple key entities, giving them shared contextual relevance through their membership in the collection. That contextual relevance is not a property of the individual keys themselves, but emerges from the parent node. Applying a set-oriented mindset in practice means shifting from implicit to explicit relationships. In relational models, foreign keys are just an alien entity property that imply connections, but in graphs, those links become edges representing direct, meaningful expressions of hierarchy and membership. For example, a category is a superset of SKUs. Each SKU is a set of products. Each product is an element of its SKU. In this model, entities no longer carry hidden attributes or foreign keys to define their context. Instead, relationships themselves carry the meaning in an explicit way, while each entity retains only its essential identity, like a proper noun in the graph. This makes the structure more natural, transparent, and intuitive for both humans and AI systems. Expanding the model shows how set theory maps naturally into graphs. A category is a superset of SKUs. Each SKU is a subset of its category and contains its own distinct set of products. Each product is an element of its SKU. These relationships are explicit and non-redundant, with meaning carried in the edges rather than hidden in foreign keys. Unlike relational models, which require multiple tables and joins, graphs express this relationship cleanly through semantic edges. The result is a structure that mirrors real-world relationships and makes data and meaning self-evident to both domain experts who understand the problem and developers who understand the solution. In the same way, LLMs or SLMs can naturally understand and reason about the structured data in applications, which now embeds knowledge. In this way, we have a common language between humans and AI. Using a set-oriented mindset with graphs can allow us to represent not only structure, but also state. For example, a store node may connect to two collections, inventory and sold products. A product state is defined by its membership in each collection. A product can either be in the inventory or be sold. The product state in the model is then defined by its relationship with either collection. In this scenario, it can only have one of them. This simple shift transforms the graph into more than a data layer. It becomes a state machine in which the system expresses its logic by dynamically altering the relationships between nodes. This is the key distinction between a static knowledge graph, built to extract knowledge, and a dynamic application graph, a living, transactional system whose relationships continuously change in response to business logic. As graph models evolve from static data stores into living, dynamic systems, they can draw inspiration and validation from nature's design principles. Nature builds infinite diversity from just 118 stable and well-normalized elements, with complexity emerging not from the elements themselves, but from the relationships, the bonds between them. Similarly, in a graph, entities act as stable atoms while meaning, logic, state, and behavior emerge from their relationships. The graph becomes alive by continuously creating and breaking connections, mirroring how life itself evolves. The key insight: life, intelligence, and purpose in graphs arise from relationships, not from altering the property values of the entities themselves. Important: once an element is created, we don't change its property values. This is one of the most significant characteristics of this new paradigm, and it will be quite unsettling for many of you who have developed systems that have functioned based on updating entity property values all your lives. When I said this was a change in mindset, I meant it. So let me be clear, I'm not inventing anything new here. This approach mimics nature's proven model. And to be fair, nature does allow for some flexibility. It appears as isotopes. Likewise, in our models, we can sometimes make slight variations to specific property values without altering the element's essence. So as long as we do not change the entity's state, contextual relevance, or meaning, we can update some property values. I hope this brings some comfort to some of you, but these should remain exceptions, used deliberately and wisely. Otherwise, the model can get a little radioactive. When models are well normalized, like in nature, entities remain stable while only their relationships change. Photosynthesis illustrates this very well. The same 36 atoms, carbon, hydrogen, oxygen, are recombined into new molecules without altering the elements themselves. Likewise, in business systems, meaning, contextual relevance, and state should emerge from evolving relationships rather than from updating entity property values. As mentioned earlier, this is the most significant characteristic of this new computing paradigm. Your ultimate business modeling goal is to design a graph that can be fully understood at any state by simply reading the node labels and edge types, without needing to look at any property value. If there is one thing I want you to remember from this entire presentation, this is it. This paradigm, no entity value updates, only relationship changes, is uniquely enabled by property graphs, which can express such dynamic behavior while preserving asset guarantees. This changes everything. Among other graph platforms I've tested, Neo4j's schema-less and strongly consistent foundation makes it exceptionally well suited for this approach. Neo4j also seems to work quite well, though it's probably not optimized for this type of workload, since this is not how graphs are used nowadays. So it can only get better. When entities in a graph are normalized to retain only their essential identity, the supporting properties are moved into their own nodes. This creates molecular-like structures, small, interconnected clusters that together define a complete business object. For example, a customer node connects to multiple addresses, payment methods, and products inside a shopping cart, forming a clear, modular pattern. We then use collections for one-to-many relationships and distinct entities for self-contained objects. This keeps nodes lean to avoid overloaded supernodes, ensuring clarity, performance, and semantic precision. As a result, each business object has a core entity node with a consistent supporting schema, much like molecules of the same compound share a formula. This shift makes graph models structured, scalable, and semantically precise, mirroring the elegance of molecular design in nature. In an ideal scenario, you should ensure that each core entity node remains consistent, with the same properties and values across all your business systems, so it can be connected rather than replicated across systems, enabling seamless integration through federated graphs. The principles of stable entities and dynamic relationships from nature can be applied to real business applications. I will demonstrate these principles in a simplified ride-hailing POC app built natively on a graph. The app was written in TypeScript and React. I am running it on Azure, accessing a Neo4j Aura database. In the app, a passenger's booking evolves as drivers engage, with each state transition captured as a relationship rather than a property update. Both the app interface and the underlying graph database show how every node and edge directly reflects the business logic in real time. Let's see the demo now.
So let's take a look at the application running. So what I have here on the left side, it's an instance of the app. And on the middle, I have another second instance. And on the right side, we have the Neo4j console so we can see what's happening on the background. So here from the left one, I'm going to select a passenger that I'm going to impersonate here for my demo. I'm going to get Peter as a passenger. And here I'm going to use the driver interface. So I'm going to select the driver. I'll get Albert as the driver. Let's take a look at both Peter and Albert on the graph. So I'll get Peter first, which is the passenger. And here you can see Peter, his main node, and his molecular structure. So he's got a wallet, for instance, right, with other payment methods. He's got favorite addresses that he has in his address book, his history, which are past, bookings that he's done. And you can see that he belongs to the passenger collection, which are all the passengers in our system. So you can actually expand it here, and you can see other passengers, right? Let's take a look at our driver, Albert. And again, you can see his molecular structure. So here's the the driver. You can see his car. He has a wallet, right, where he might have a payment, the way he's going to be paid. He has his history, there are past bookings that he's done, and this is his car. He's connected to the car, and the car is connected to him, and the car is now available. These are states. This is the fleet superset, and these are the other subsets that represent states on where the car can be. So let's go on and run our demo. So our passenger is going to make a booking, so it's going to select an address. It's going to get, let's say, this origin, and this is the destination. And he's now going to make a booking. And you can see here on the driver interface that you can already see, the Peter's booking there on the waiting. So let's go take a look at the passenger, see what happened here. So now you see that Peter has an active booking. You have this relationship has been created. We can take a look at the booking. And you can see the booking now has an origin and a destination. It is now on a waiting state that's connected to that waiting collection. You see the relationship with the passenger and the booking are here. He has an active booking, that's a state one, and there's one from the booking to the passenger to show that that's part of the booking information. So what's going to happen next is that Peter, right, he's going to go and select that that booking. So he's going to go and accept it. So we're going to query here again, and you can now see that that booking now has a car, right? So now he's active. It's not waiting anymore, right? And you see that that car. I'm going to do this. I'm going to get the information from this booking. I'm going to get the booking number, so we can now start tracking the booking. So I'll put it here. Now you can see that that booking is active. You can see the car now, it's on a busy state. And what's going to happen next is that Albert is going to start the ride. So far he's just accepted it, but he's not picked up the passenger yet. So the moment I do that, I'm going to click here, the state is going to change, right? So now we have another relationship between the booking and the car. You can see it's been picked up. You can take a look at what timestamp when he was picked up, so that can be used for the auditing. And lastly, we're going to drop the passenger at the destination. So we just click here and we requery the booking. Sorry, the booking. And now the booking is connected to the past. It's not active anymore. You can see the car is now available, right? And that booking is now part of the history of both Albert, which is the driver, and Peter, the passenger. Right? And that's how we conclude the whole process here. So let's go back and take a look what went on.
The process begins when a passenger creates a booking by specifying the ride's origin and destination. The system calculates the fare using a dynamic pricing formula likely sourced from a microservice developed using the traditional computing paradigm, the ENIAC computing model. So yes, you will end up using the best of both worlds. For calculations, we use the model that was built for that, and for interactive workflows, we use this new approach. Once we have the pricing for the ride, a booking node is then created with its molecular schema, capturing details such as passenger, timestamp, route, fare, payment, and initial waiting state. A relationship is established between booking and the passenger. From this point onward, the booking entity itself is never updated. Instead, its state evolves through relationships by deleting and creating edges that reflect context. This illustrates the graph model's elegance. Data isn't overwritten, but evolves dynamically through connections, mirroring how change occurs in nature. Drivers query the waiting collection to see available bookings. When a driver selects a booking to serve, the system doesn't update the booking or car node's properties. No set command whatsoever. Instead, it deletes and creates relationships to reflect the new state. The booking moves from waiting to active. The driver's car moves from available to busy. A relationship is added between booking and car with a timestamp for auditing. All of this happens within a single ACID transaction, ensuring only the first driver to claim the booking secures it. That means only the first driver to delete the relationship between the waiting collection and the booking secures it. This demonstrates how business logic emerges from relationships in a property graph, enabling real-time state transitions without mutating entities, turning the graph into a living model of business behavior. When a passenger is picked up, the system doesn't update a status field as in a relational model. Instead, it creates a new picked up relationship between nodes, with a timestamp capturing the exact transition. The booking and car nodes remain unchanged, only relationships evolve. This approach makes the graph a living system where events are recorded as structural changes rather than overwritten data. As a result, the whole history of state transitions can be reconstructed at any time simply by traversing the edges. When a trip ends, the booking is closed entirely through relationship changes, not by updating fields. The booking is added to both the passenger's and driver's history collections. It's also moved into the system's past collection of completed rides. The car returns to the available collection. The has active booking relationships between booking, passenger, and car are removed. All of this occurs in a single ACID transaction, ensuring consistency. The key principle is that the system doesn't overwrite data, it evolves through relationships. This makes the graph itself the source of business logic, workflow, and integrity, keeping the front end thin while the relationships carry the meaning, much like in nature. Take some time to look at the graph in this slide. You can read it and understand what is going on. You can tell that a passenger booking has been served by a car, although the passenger has not been picked up yet. You can reason just by reading the node labels and edge types. We finally have a common language that both humans, regardless of their domain, problem, or solution domain, and AI can understand. In this way, your AI systems will be able to reason and act on the structured data, which now also has knowledge and logic. And if you allow, AI can even run your systems. If you come from a knowledge graph background, you may criticize this model for not being well optimized, and you are right. However, what you need to consider is that unlike knowledge graphs, which have a single user, the data scientist, this is a multi-user business application graph. Therefore, the most commonly used data for each user's use cases must be within a few traversals of their personal anchor node. In this case, the passenger, driver, or back-office user. So you will have to look at graphs in a new way and model them to be a multi-user business application graph. There is much more to this, but I will not have time to cover the model's particularities. The model is guided by 5 core design principles that make graph systems simple, scalable, and accurate to reality. 1. Proper noun nodes. Nodes represent unique entities, and their properties should contain only the essential ones that define their identity. State and contextual relevance are expressed through relationships, making the graph tell a story rather than hold data. 2. Lean nodes. Keep connections minimal by using collections like bookings, fleet, history to avoid overloaded supernodes, ensuring scalability and clarity. 3. Read-only nodes. Nodes are immutable once created. Property values aren't updated for business logic. This immutability simplifies concurrency, consistency, and debugging. 4. Don't delete nodes. Data is never erased, only relinked. This preserves full history and auditability. 5. Relationships drive the system. Business logic lives in the graph structure itself, not in application code. The front end expresses intent, while the graph enforces rules and consistency. Key insight: this architecture unifies data and behavior. Instead of CRUD operations and table updates, systems evolve through mirroring how nature models life. That is the true power of property graphs. This brings us to our conclusion. As you probably noticed, this isn't about replacing RDBMS and SQL with Graphs and Cypher. It's about changing the mindset. Graphs aren't just amazing analytical tools. They have tremendous potential to become the next generation of transactional systems where understanding and action happen in real time, not after the fact. To get there, we need to unlearn the old tabular mindset where transactions mean changing isolated records and relearn a graph-native one where meaning comes from evolving relationships between stable entities. That's exactly how nature works. Unchanged elements, constantly reshaping their relationships. Think in sets, not tables. That's nature's logic. Graph-native systems are the missing bridge between humans and AI, a shared, intuitive language of structure, meaning, and reasoning, where data and knowledge finally become one. The code and Cypher script for this demo are available in my repo. You'll also find a more complex tendering system with multiple workflows intertwined and AI agent simulations covering processes such as vendor, tender, and bid vetting, as well as multi-level approvals. Since 80% of business apps are workflows, this tendering system illustrates the model's broad potential for business use. You can also find many articles I've written about this new approach to developing graph-native business solutions on my Medium page, as I have only scratched the surface of this approach today. There are several rabbit holes I did not go down due to time constraints. And if you have questions or would like to discuss these ideas with me, please do. I would love to hear your thoughts. Here is my email and LinkedIn profile. This was a highly condensed distillation of 10 plus years of thinking, ideating, modeling, and development presented in 25 slides and 30-minute talks. So I don't expect that you were able to assimilate all of it. You should have a lot of questions. If you don't, consider seeing it again. You will need more time to digest all this and think it through. Take your time. At some point it will click and your mind will begin to rewire. You will start to understand how all this works. It will grow exponentially from then onwards, and you will start to see the world through a different lens. When that happens, there will be no way back. It's a fantastic journey. Thank you.